Okay, hi there. First, thanks to the whole REcon team for having us here, and we're jumping right in. So first, we're Mariano, Graziano, and Jonas, zaddach. We both did our PhD in the south of France, got hired by Cisco, and are now security researchers in Talos and working with ClamAV. This is the antivirus scanner of Cisco, and this brings us right to the topic because we want to talk about threats. So the threat landscape at Talos looks the following. We have 1.5 million samples coming in every day, and we need to decide for those samples if they're malicious or non-malicious. Because doing this manually would be too hard, we have a pipeline set up where we first scan the samples, and first we will scan them with ClamAV to determine which samples are already detected as malicious, because those samples we don't need to look at anymore. The samples that are detected as not malicious go to our sandbox threat grid and are executed there dynamically. The sandbox gives us indicators of compromise, and depending on how many indicators of compromise we get, it will be, the sample will be identified as malware or not malicious. Now, the problem that we have are those samples here, because ideally, we want to have malware identified already here at this stage. So what we need to do is to write a signature for the antivirus so that next time the sample gets detected here instead of just at the sandbox. The problem with that is that you need a lot of signatures to do that. So in the period from February to April 2017, we published over 560,000 signatures, which amounts to about 9,500 signatures daily. Of course, not all of these signatures are written by humans. Most of them are automatically generated. But the thing is that those automatically generated signatures are mostly hash-based at the moment. And ClamAV supports mainly three types of signatures. There are hash-based signatures, where one signature identifies one file. There are pattern-based signatures, where a pattern determines if the content of a file is malicious, so several files can be identified by one signature. And there are bytecode-based signatures for the really hard cases, where we basically have a Turing-complete program that is running inside ClamAV and can inspect and analyze files. The hash-based signatures have the drawback that you have one signature per file, so the catalog of signatures grows very fast. And this means that the ClamAV scanner on every instance needs a lot of memory. On the other hand, the bytecode signatures have the disadvantage that they need to be executed, so they need a lot of computational resources. And the sweet spot in between are pattern-based signatures, which are a good trade-off between memory usage on the client and computational resources. Now, this is the point where BASS comes in, because we want to transfer the weight from those the load of hash-based signatures into pattern-based signatures. How do we want to do that? So we start with malware clusters that we get from other systems. We inspect and unpack the files in those clusters. Then we filter the files out that we cannot treat in BASS. Finally, we generate a signature, which we then evaluate to see that it only covers malicious files and no goodware. And we publish the antivirus signature. So this was the high-level overview. Let's go a bit more into detail. First, clustering. Clustering is a step that comes before BASS. We have several sources for clusters in Talos. First of all, our sandbox indicators of compromise, where we cluster the indicators to have similar families. We can use structural hashing. If we have one malicious sample, we observe the properties of the executable and try to find executable with similar properties. We gather samples from our spam campaign datasets, where the same spam campaign probably carries similar samples, and several other sources. Now, the sample comes into BASS, and the first thing that we do is to extract the contents, because the extracted form will be likely much better for signaturing on than the compressed form. ClamAV can extract a huge amount of files. First of all, zip archives, all other kinds of archives. It can extract email attachments, but it can also extract packed executables like the UPX packer for PE files. And it can extract nested documents. So if you have a Word document that drops a portable executable, then ClamAV can already extract this portable executable. Once the extraction step has finished, we gather information about the files about the file artifacts that we have now. This information can be file size, MIME type or magic string, hash, and so on. And this information we use in the next step, which is filtering. Here we want to filter out files which we cannot read in BASS. So, for example, we have a cluster which contains mainly Windows executables for the x86 architecture, but some executables with MSIL code snuck in, the Microsoft Intermediate Language. We cannot handle MSIL in BASS, so we want to filter those out. Or the other example would be that we have some JavaScript files, and we want to reject those clusters outright if they consist of JavaScript files, because this is not the focus of BASS. So let's go to the interesting part, the signature generation. In the signature generation, we first disassemble the executables. Then in the next step, we try to find common code. Then for this common code, we need to find the longest common subsequence. I will go more into detail what that is in a minute. And finally, we generate a signature. So disassembling is pretty straightforward. We use IDA Pro as a disassembler, but we kept the interface to the disassembler intentionally general so that we can plug other disassemblers, maybe Radar or something else in the future. The next step is to find common code. So the idea is that we have a cluster with samples which have functions, and we want to find those functions among the samples that are similar. The thing that we do for getting that is we apply a binary diffing to pairs of samples. If we have a small cluster, we can compare each sample with each other. If we have a larger cluster, we need to prune some of the comparisons. And once we have the diffing information, we can build a similarity graph between functions. So, for example, here you have function 1 from binary 1, you have function 1 from binary 2, and function 2 from binary 3. And those form a cluster that is connected with pretty heavy weights. You can see here 1.0, 0.8. We have a second subgraph that is just consisting of two functions, and the connection is weaker. So we choose this subgraph for going on with the signature generation. Now, there is a slight drawback. We might have chosen a function that is just statically linked in library code. To prevent this, we use Camino, which is a code clone search engine that is developed here at McGill University in Montreal. And we have all the functions that are from clean samples inside this database. And we simply submit our chosen function here from the last step to this database and query if there is any similar function inside. If the function is whitelisted, we discard the chosen function, go back to the last step, choose the next best subgraph, and carry on. Now, we have functions between the samples that are similar, and what we want to do now is we want to generate a ClamAV signature. ClamAV signatures, fortunately, are very similar to longest common subsequences. Don't confuse longest common subsequences with longest common substrings. Longest common substrings, I don't know if you can read it well here, are characters, strings of characters without anything in between in the substrings, while longest common subsequence allows to have other characters in between. So for example, you have ABBAC here, but here it's ACB, but it's still a longest common subsequence inside this string because all the characters are present in the same sequence. Okay, and to get this longest common subsequence, we used the Hamming KLCS algorithm as described by Christian Blichmann in his thesis. This algorithm works as follows. We have we compute the Hamming distance between all the strings that we currently have. And then we apply the normal LCS algorithm in a dynamic programming version, because we want the naive algorithm is very resource intensive. The dynamic programming version trades off more memory usage for less computational resources. And we apply this to the string to the two strings with the lowest Hamming distance, and keep the resulting longest common subsequence, and then repeat the process. So to make this a bit more graphical, here we compute the Hamming distance. The Hamming distance, just to remind you, is you look at the characters at the same position. So for example, AA are the same, so you add 0 to the Hamming distance. You look for BC, they're different, you add 1 to the Hamming distance. So you see this string has 8 distance, this one 12, these two, and this one 11. So we keep the ones with the lowest Hamming distance. We run the LCS algorithm on them. We extract the longest common subsequence. We discard the two strings, just keep the longest common subsequence, and then we repeat, run the longest common subsequence, get one longest common subsequence, and we're done. Okay, so this is almost our ClamAV signature, but not completely yet, because the strings, when you embed this sequence in the strings, it can actually have gaps in between where other characters fill in. So first we need to find those gaps, and you see that we replace them with the wildcard character here in the ClamAV signature. And then a particularity of ClamAV signatures is that we cannot have single bytes between two wildcard characters, so we discard all the single bytes. And then the cherry on top of the cake is that we use AV class to automatically generate a name for our malware cluster. This works by going for all the samples to VirusTotal, querying the antivirus labels, processing it with the AV class algorithm to get a common name, and then using this name. So for example, here you see the name, you see file type 0, which is just all files in ClamAV, and the signature. And this signature matches our example files here. So you can see that it corresponds there. Okay, so now we have our signature, but we still don't know if it's any good. So we need to do testing. And the first testing step that we do is false positive testing. We have a huge set of known benign binaries in Talos. We run the signature against those ones to see that it doesn't trigger. If it would trigger, we would add the binary that we found, the benign binary, to the set of whitelisted functions and reiterate the process. And a final step is manual validation by an analyst. For this, we leverage the Cask plugin that we extended. Normally, the Cask plugin is to generate a ClamAV signature from an IDA file. We have turned the process around. We give it a ClamAV signature, and it's highlighting the parts in the binary file in IDA that triggered the signature. This plugin will be released with this functionality later next week. The technical implementation of BASS. BASS is based on Docker and Python. There is one central Docker container here with the BASS code in Python, which controls all the tools that we have. So IDA-Pro for disassembling, BinDiff for binary comparison, and Camino for the whitelist database. And you speak with the BASS container with a small Python library that calls the remote APIs. Okay, so it's time for the demo.
Okay. So at this point, you should have an idea about the technical implementation, so all the different components, and you should have also an idea about all the backgrounds that you need to interact and understand the BASS components. So now let's have a look at how all these works together. So 1 second. Okay. So first of all, as Jonas said in the previous slides, okay.
Away, no? Up.
Up. Okay. So like Jonas said before in the previous slides, everything is run with Docker containers. So in order to run multiple Docker containers at the same time, we use Docker Compose. So how Docker Compose works is that we have a Docker Compose configuration file in which we specify the services. that are the different containers that we want. In this case, as the previous slide said, we have like the BINDIF containers containing BINDIF and IDA Pro. Then we have the BASS, and then we have Camino. The additional entries here specify, for instance, the volumes that we want to mount inside the containers, or the ports that we want to be exposed to the host, okay? And then, for instance, some environment variables, for instance, the virus total AP key that we need for the label generation using AV class. Okay, so now, as in the previous slides, we have this client that interacts with the only exposed containers, that is the BASS container. So let's try to have a look at the client. So the client is developed in Python. We have different classes. As we can see here, we instantiate the BASS class with the URL, and the URL here is the URL of the BASS server. Then we create a job, where here the concept of job means that is all the operation that interacts with BASS, and then BASS interacts with the BINDIF and the Camino container. Then we add the samples from the cluster, okay, in order to process the job. We submit the job, and then we wait until the job is it's over, and this takes a couple of minutes. At the end, we get or a signature, okay, or we get some error. In case everything is successfully, we check the result, and the result contains our signature. But sometimes it's also good to directly go through the command line in order to do some tests or add additional features. So for instance, here is an instance of IPython. Okay, so here I import the client, I instantiate BASS with this URL for the BASS server. I create a job. I add two samples just to test if everything is working. I submit the job, and then I wait. And here this takes a couple of minutes. Then here I list some methods that are useful from job, and the interesting one, for instance, here is the result. And here we have a JSON containing the signature. Okay, this is the ClaimAV signature in NDB, an NDB ClaimAV signature. And here, for instance, we had the two samples, and we had with this signature 100% of coverage for all of them. So now let's see how this actually works with the real client, okay, that has more additional features. Okay. So the normal client, the important parameters, here the samples, it needs a list of samples that we specify, okay? And now we look at two examples for real malware families and how we automatically generate a ClaimAV signature for them. Okay, so here we have the client. We specify the directory containing the samples that we need, and then the client starts, and here we have the list of the different samples that we are feeding our system in order to automatically generate a signature. Okay? Then here I stop it because it takes a couple of minutes, but at the end we got from the JSON an NDB signature, that is this one, is a normal ClaimAV signature. Then if we run it with a ClaimAV, we run the clam scan command, okay? Here we can see that it triggers a couple of times. In particular, here it triggers 32 times over 51 samples, so this roughly means that it covers the 62% of the entire cluster. That this can be either satisfactory or not, it depends on our needs, okay? Then, here is the same for another family, okay? Again, in this family, we specify the directory. Again, we have the list of all the samples that we want to cover, the BASS server. And again, we generate the NNDB ClaimAV signature. We run clam scan, and this time we have, for the 9 samples, 100% coverage, okay? But now it's important, as Jonas said in the previous slides, to validate this signature. I mean, to understand the goodness of this signature. So this signature has been generated on some function that is peculiar to the malware or some function that are from the library, okay? So for this reason, at the beginning, what we were doing is, like, for instance, manually checking with IDA. So we open the sample on IDA, we do a binary search with the first byte, okay, of the first bytes of the signature, and then we end up finding the so the function in which the signature was triggering, okay? And then we manually inspect this function to try to understand if it's a library function or is a real peculiar function of this family. At the end, we understood that we were doing this over and over, and we decided to have an IDA plugin called Sigalizer. Okay, in this plugin, here you paste in Add the Signature, you paste the claim AB signature, okay, and then it automatically covers and colors over the basic blocks that are involved in the signature, okay? Like you can see here the entire signature, the signature for this malware, it's covered the entire function, and you see all the basic blocks that are involved. And this is really useful when you want to debug. Talking about debugging, sorry, okay, here it is. Talking about debugging, if you want to debug here something, with the BASS framework, you can use the command line. Under temp, you have the BASS logs directory containing all the logs. And so you see all the interaction, for instance, as you can see here with, for instance, the bin diff containers for every sample submitted. And you have all the message. So this is a roughly idea about what the BASS framework can do. And now let's go back to the presentation so Jonas can continue from the current slides.
Yeah, so we're coming towards the end. Before I finish, I want to point out that there are some limitations with the framework. It only works for executable files, but this is by design and will not change. Also, it does not work well for certain types of malware. So things that we don't cover very well at the moment are file infectors, because they inject small pieces of code across a benign binary, and those pieces of code vary a lot. So we need to find a better strategy for those ones. And also backdoors where you have a huge binary that is benign and has only one or two malicious functions are difficult to handle at the moment with BASS. So our idea is that we want to filter out those types of malware in the future already before throwing them into BASS. Also, please remember that the framework is in an alpha stage, so expect some rough edges, but if anything goes wrong, we're there to help you. Just contact us and we can get over it and help you with it. So we presented you an automated signature generation system for executables. And the cool thing about this is that we implemented a lot of research ideas that have been around, but were not available as code. A huge inspiration for us has been VX Class from Zynamics, but then Zynamics got bought by Google and VX Class disappeared, so it's not available anymore. And because we want other people to look at this and give us comments, the code will be available open source. So everybody can try it, improve it, give improvement suggestions to us. And it will be available in just a few minutes at this URL. We're going to put the repository live just after this talk. And yeah, that's it. Thanks for listening, and welcome your questions. Questions?
It's very cool. I just had a question about Camino and how you used it. I was just sort of Googling around on Camino. Does Camino provide does it provide a database of signatures or static libraries, or did you have to populate that yourself?
No, we have to populate it ourselves. Also, one thing is that the API of Camino was not that evident. So one thing where I see also added value in what we're doing is we added APIs and Dockerized versions of the tools, so other projects can use the components that we have and use them easily.
So you made Camino better?
We were corresponding with the author, and yes, some improvements directly went into Camino.
Thank you.
You say that you cluster the malware first. Can you tell me approximately what is the size of your cluster and how long does it take to run?
So at the moment we're using rather small clusters, like 20 to 50 binaries. And this takes about, I don't know, 10 minutes, 15 minutes to run. Yeah. So the thing that is the most limiting is the number of comparisons you have between the binaries, because each of these needs to run. And you can parallelize the comparisons, but then the number explodes very quickly because it's 2 out of n.
If you have a true 0 day, then how does it work? That doesn't fall into a cluster. Then how do you handle that case?
That's not the focus of BASS. So we need to have a cluster first. Without a cluster, nothing works.
Gotcha. Okay, thank you.
Over here? Is this on? Okay. One question over here. I'm waving. You can, over here.
Yeah.
You said that you were querying VirusTotal to be able to generate your names. Could you describe a little more of the technical process of what that query looked like and then how you assimilated a title for everything?
So the query is we just take the hash, go to VirusTotal, get the file report for that. And for this, we get all the antivirus names, so antivirus vendor plus signature name. And then we use AV class, which is a paper presented in 2015, I think.
Okay, there is AV class that is this project. So once that you download all the reports, AV class process them, and if it's possible, try to generate a common name, okay? So it parses the VirusTotal reports, is a research paper, and the code is on GitHub, and we simply use it.
So the AV class takes the components of the names, tries to extract common things like worm, virus, and so on, normalize this, find a normalized name across all the AV labels that exist, and then give you one label that is used by most of them, most of the AV labels.
Okay.